Well, thanks for coming today, those of you that are here and made it. And it's a pleasure to talk to you as usual. Today, Sylvan and Einat asked me to talk about ordinary differential equations, and it's sort of a rough topic for some people, and I'm hoping I can simplify it a little bit. But as Sylvan said, it's super important in volcanology. If you look back at the literature, even since 1980 or 1990, you'll see a lot of people became famous by applying ordinary differential equations in volcanology. People like Oleg Melnik, who has worked on a lot of problems and sort of conduit dynamics and magma chamber dynamics by applying ordinary differential equations to those problems. Andy Woods and Herbert Hubbard, they're two people who published a lot on plume dynamics and box models for fluid flows and that sort of thing using ordinary differential equations. Steve Sparks, way back in his dissertation, said, hey, bubbles are important in volcanology. And he solved a lot of those problems using ordinary differential equations. So the list goes on and on. Giovanni Macedonio, Antonio Costa, they've done a lot with ordinary differential equations. And there's actually a lot more to be done. And I think it's fair to say that, some of those people are fantastic mathematicians. And some of them are kind of normal mathematicians or even normal geologists. I won't name names, but the idea is you can use the methods that mathematicians and computer scientists have developed to help you formulate problems. And I want to show you a little bit about how to do that today, at least to take the mystery out of how people come up with the equations they do to describe volcanic processes, and maybe spark your interest. Maybe you'll get into developing some systems of equations of your own and trying them out, and you might make the breakthrough, right? So it's pretty important. A lot of the notebooks I'm showing you today actually come out of numerical methods in this book. And if you've never heard of this book, you should. It's one of the most cited books in science. Last time I checked, there were something like 60,000 citations or something to this book. And it's, as the name implies, it's sort of a cookbook of numerical methods. And the one I showed you is in C because I write a lot in C, but there are numerical recipes in other languages as well, so you can check, or even sort of generic ways to do it. You can definitely look at Python or something like that. You can find a lot of numerical recipes in Python where people have taken the algorithms in this book and recoded them in Python and that sort of thing. So the reason it's so popular is the explanations are so clear and the applications are so meaningful for people. So I recommend it. Anyway, let's get to it. I'm going to bring up a few notebooks. These notebooks are in Victor in your folder, right, Sylvan? I haven't looked actually, but I think they are. And I'm going to talk about.
If you look in the week 7 folder, so you're doing shared Victor courses. Spring 2025, and then you have a week 7 folder, and the 3 notebooks are in there. So you can copy and paste them into your home directory, like we're doing every week, and you should be able to run through them and edit them.
Okay, cool. And you guys can see my screen, right? It says Victor.
Yep.
Intro to. Okay, great. Ordinary differential equations. Okay. So I'm just going to start simple with some numerical methods for solving ODEs, as they're called. And I'm going to cover a few methods in this notebook. One is about Euler's method for solving ODEs. It's not actually used very much, but Euler was sort of the first person to come up with a algorithmic way to solve ODEs, and it's sort of historically important. And maybe it's the simplest thing to understand. So there's nothing wrong with using Euler's method. In fact, several codes I know of that solve for ballistic transport for pyroclasts use Euler's method. They don't bother going any further in that.
PDC
but then
as
there's
well.
some,
There's a few PDC models that are still using, Eulerian phase for many things.
okay, yeah. Okay. And then there's the Runge-Kutta methods of solving ODEs, which are a little bit more sophisticated. We don't really need to understand the details of what's happening in Runge-Kutta. They're two scientists who worked on basically developing algorithms to solve ODEs, which approximate analytical solutions more closely, and so they're sort of more accurate. And then I'm going to give you a classic example of ODE modeling from magma reservoirs. It's called the tank problem. And like I said, I got a lot of this out of numerical recipes in C, and I took some of the Python code for the Runge-Kutta method from some lectures by Kai-Feng Chen at Taiwan University. Those are also some awesome lectures to check out if you're interested in more in this topic. Okay, let's start with an ordinary differential equation. You've probably seen this one. This one might be applied to, say, radiometric radioactive decay in the nucleus of an atom. So it's used in radiometric age determinations, isotopic dating, and that sort of thing. It's used in all kinds of population dynamics, disease, transport, and that sort of thing. So anyway, the main thing about a simple ordinary differential equation like this one is that I've got the rate of change in some variable, dy as a function of dx. So maybe x is time, for example, in this, or it could be a spatial dimension or whatever. And dy is changing as a function of that index variable. And that's equal to usually some constant. I've just shown k there. You can take or leave k in this case if you want to. And y, the main thing is y is on the left-hand side of the equation and on the right-hand side of the equation. So basically, this is just saying that if you want to know the rate of change in something, you have to know the current amount of that thing. So if we look at population dynamics, the rate and change of people depends on the current number of people on Earth, right? I mean, it's pretty straightforward. So the idea is we can start with an initial condition, say y equals 1, time equals 0, x equals 0, or whatever, and when we can solve it, and dy dx equals ky, or just equals y, is pretty classic in sort of a first ordinary differential equation because it's got an analytical solution. You can just integrate both sides of the equation and you get y equals e to the x, or e to the kx if you include your constant. So that's the origin of essentially exponential growth and what people refer to as exponential growth or exponential decay if k is negative or something like that. So if we take a classic example, if y is the number of rabbits and you're interested in the change of number of rabbits over time, then you can think of that as exponential growth. And here's this beautiful image. I'll bring this up in a new tab just so you can see it. Let's see, open image. It's not letting me do it. Weird. Why aren't you letting me do it? I don't know why it's not letting me do it. Anyway, you can see this picture of rabbits multiplying on volcanoes, but that's the idea there, right? So there's some philosophical background on Eulerian and Bernoulli's work on E and that sort of thing. But let's just solve it. So you guys know how to do this in Python already. I'm just going to use NumPy and Matplotlib, and I'm going to look at x over a range from 0 to 10, say at 0.1 intervals, and I'm going to plot up the numerical solution, and so you get exponential growth in the number of rabbits as a function of time, right? And K is just going to scale what that time dimension is in this problem, and I'm just sort of ignoring it right now. So that's our analytical solution, and but most of ODEs, it's hard to solve the analytical solution, or you have to make simplifying assumptions for the analytical solution, or maybe there is no analytical solution at all. So as a result of that, we developed some numerical methods. And so one of the first numerical method for solving an ODE was done by Euler. It's called Euler's method. And it's not really used, and it's not really used because it's error prone for the most part, but it introduces uncertainty. You can see the equation here and why it introduces uncertainty. Say you're interested in y at time equals like 1 at the interval +1, I +1. So on the left-hand side of the equation, I'm just saying, well, what's time 1 interval in the future? And that's going to be equal to whatever y is now, plus some function, fxy, which is my differential equation, like dy dx equals y, and then h is my time step for approximating this solution. And so if the time step is large, then I'm going to have increasing error in this solution. And the longer I extrapolate into the future, in this case, is function of time, my total error is going to increase, right? So you guys know this if you like take a compass and you go outside and you measure a bearing to a tree or something like that, and then you measure the bearing to the next thing and the next thing and the next thing, your errors add, right? So even if you're only off by 1 or 2 degrees when you take a bearing, if you do that 10 times, suddenly you're off by 10 degrees or more. And so that's a problem with solving this equation using Euler's method, is that since it's a simple formula basically and a simple approximation of the differential equation, it's prone to errors. But nevertheless, let's check it out. So I'm going to implement Euler's method in code, and I'm just going to use that same expression, dy dx equals y, and I'm going to start out with the initial condition, y equals 1 at time equals 0. So I'm going to use NumPy again for some of this just to calculate the analytical solution. But I'm going to create a function here, and all of these methods that I'm going to show you today use functions to represent the differential equation. So in this case, it's really simple. My function f of x and y just returns y, right? Because dy dx equals y. So that's it for this particular one. It's super simple. I'm going to start with the initial condition, x at time equals 0 or x equals 0, y equals 1. And I'm just going to select some step for my Euler solution. And I'm going to continue for, say, 10 till time equals 10, right? So I'm going to go through this while loop, and I'm going to, while x is less than 10, I'm going to set k equal to the function. Y is going to increment by h times k1. That's just implementing this function up here. I think that's no problem for you guys. And x time is changing by h, right? Because that's my time step. My exact solution, again, since this one's got an exact solution, is just e to the x. So if I run this, let me just run it. It says to me that using the Euler method after we reach x equals 10, my value has gone from y equals 1 to y equals whatever that is, 21,000 and change. And the exact solution is 22,000 and change, so that's a difference of 1,000, right? So that's my approximation. Now I can improve that, of course, by changing my step, if I make my step double not 1 and I run it, then I improve my difference. I change the step by an order of magnitude and I improve my solution by an order of magnitude. So for some people that's good enough, right? You know, I can keep going and I can try to reach an exact solution. And I'll never quite make it. I'll always have some uncertainty. Of course, as this increases, the difference is going to become greater, right? So you can see that by the time I get out to a large value of X or a larger value of X, I've got pretty big differences if that's my step. And that doesn't even really improve that much if I increase the or decrease the time step. So that's the kind of thing I run into. The Euler method is good for extrapolating kind of a short time into the future, but it can lead to some problems as I move along. So that's, but it is a solution to the differential equation, right? Okay, so along come Runge and Kutta. And the Runge-Kutta method is doing exactly the same thing that Euler does, except they're like, hey, we want to improve on this method. And basically they're just two clever people, and they said, okay, well, we're gonna divide this into steps. We're gonna add a step in order to improve our use of extrapolation here, our extrapolation method. And this is how it works. So I define K1, just like I did before, is equal to F of XY, whatever my ordinary differential equation is, right? Whatever the right-hand side of the equation is. In this case, it's just Y. And K2 then is going to be the solution to that function for X equals 1/2 and K1 Y half. And then at Y I plus 1, I'm going to use, instead of using K1, I'm going to use YI plus HK2. So this is just a way to sort of better approximate sort of the rate and change of that slope of that line, of the exponential growth in this case. So if I do the same thing, and this is now called a second order Runge-Kutta equation because I've got K1 and K2. And in this case, I'm literally just implementing that equation just like I did before. And I'm gonna use the same function F. Sorry, in my notebook, I didn't repeat it here, but that's the same F is up here. Define F as return Y. That's it. And so I'm going to run that, and I get a solution, and H is 0.01. I'm running it for 10 time steps. And you can see I've improved. I've gotten closer to the exact solution just by implementing this one extra step. And that's sort of the magic of the Runge-Kutta method in solving the ordinary differential equation. So up here, I don't know where I wound up. Yeah, I think this is the original thing. I was off by 1,000 rabbits after time 10. And if I go down here, I'm off by 3 rabbits. And so maybe that's acceptable to me. Maybe that uncertainty is pretty good. And of course, I still have the same problem. If I increase the runtime, I increase my error, right? And so I can't go too far into the future here. I still have the same sort of problem in solving the ordinary differential equation because I'm approximating that math, right? And so even if I don't have an analytical solution, I can be sure I'm going to be off at some point in the future by some amount because of the way the solution is found. So this devolves into just more and more detailed methods for improving the approximation. And I'll just sort of quickly show you two. So one is the second order equation. And you can see all I've done, the fourth order equation. And so all I've done is now I've got K equals 1, 2, 3, and 4. And this is further approximating the solution. And so now I'm sort of making some actual improvement. If I you know, have the same parameters as I did before, I've essentially got no air left. And even if I change this to 100, oh, I still blow up. Darn. Okay, my fourth order solution. So you can see how far I can go. If I want to go up to 100, maybe I can. What if I improve that? Oh, did I cheat? I think I did cheat there. Okay, let's do that. Okay, it's an improvement. So I'm doing better in my solution. And then finally, I can do something called a fifth order Runge-Kutta method. And this gets to be really gnarly looking, honestly. And the coefficients in this equation are found using something called the Cash-Cart method, to other people who worked on this problem. And so now my solution is looking a little bit strange. Got a little bit more complicated. For one thing, I've had to specify these coefficients, and these coefficients, like 2825 divided by 27,648, where does that come from? Well, that comes out of this Cash-Cart method for solving the Runge-Kutta approximation. The other thing that happens here, as you can see, I put in a second loop. And so while x is less than 10, that's just the way it was before. Now I go through while true, and I adjust my sample spacing depending on the error. I adjust my time step depending on the error. And so that helps me a bit. So I'm going to run that, and you can see that I'm getting relatively little error. I've now taken 4,091 time steps to get to time t because I keep adjusting the time step, and that's improved on my difference. So things just get better and better as I implement these methods. So let's see what happens when I go to 100 here. Oh, I still have some error. So that's the thing with my interpolation to my approximation for these solutions is I can run into real problems if I try to extrapolate too far into the future with something like exponential growth, where the numbers get very, very large. Okay, that won't be so bad if like K is limits the rate of growth. So, you know, an example of that just in public health would be COVID, right? So when COVID was transmitted, people were worried about exponential growth, that is exponentially increasing the number of people who get the disease. But K was a factor of like 1.1 or 1.2. So for each person with COVID, maybe in a 1 week period, they would infect 1.2 other people or something like that. So the growth was less. And all ODEs are used to approximate that kind of spread as well. Okay, so let's you guys have put up with me for half an hour now. Let's go to a volcanological example. Okay, and I'm going to start with something which is called a tank problem. And a tank problem is an example of a tank problem would be this morning I turned on a coffee pot and water dripped through the coffee, and the question is what's the concentration of coffee in my cup after the water passes through the coffee reservoir at some rate, right? That's a tank problem. You can think of a magma reservoir the same way. So in this example, I've got a magma reservoir, let's say it's 0.1 cubic kilometers, and it's got a basalt. This is an example from Hawaii, actually, from Kilauea volcano. So we've got a magma reservoir of 1/10 of a cubic kilometer. It's some high level reservoir or whatever. And it's got basaltic magma in it with a density of 2,800 kilograms per cubic meter. So we can think of our reservoir in terms of the total number of kilograms, right? And let's say the volcano is erupting at a low rate, say 5 cubic meters a second, dense rock equivalent. And a primitive magma is being supplied to the reservoir at 5 meters per second, right? That would make sense. So let's say you're at the surface and you're monitoring an eruption, but you're seeing zero deformation. That means magma is leaking into your sort of upper shallow reservoir at the rate it's coming out, but maybe the magma coming in has a different composition. So let's say the original magma reservoir has a composition of like 8 weight percent MgO, and then we've got primitive magma that's leaking into the reservoir at 16 weight percent MgO, right? So it's just a more mafic, more primitive magma in that case. So if that's the situation where you've got 8 weight percent MgO in the magma chamber initially, and you change the concentration by leaking 16 weight percent MgO into the magma chamber, you expect to see the lava composition change with time. And so the lava composition is going to increase in MgO concentration as a function of time. And the question would be, well, how fast is that MgO concentration going to change? Must be a function of the difference between 8% and 16%, the flow rate, 5 cubic meters a second, and the volume of the reservoir, right? Because that's going to affect the concentration. So you can ask yourself that question, and we're going to make a simple differential equation. So we're not going to consider any other mechanisms for MgO gain or loss. So we're going to ignore crystallization in the magma chamber. The magma chamber is going to be well mixed, blah, blah, blah. If you read a lot of the literature where you're using ordinary differential equations, you always got to search around for the paragraph or so where it's telling you, hey, I'm making a lot of assumptions. So that's what we're doing there. Okay, so let's solve it relatively quickly. I'm going to take this and I'm going to say let x of t be the mass of MgO in the magma reservoir at any time. So the mass of MgO, that is how many kilograms of magnesium are in the magma reservoir at any time t. That's the kilogram, then I can calculate the kilograms being released at the surface and the lava flowing. Since I know these volumes, I can calculate the concentration. Okay. And so the rate of change is, dy dx, or dx dt, sorry, or I can just say x prime dt is the rate at which magma enters the reservoir minus the rate at which magnesium erupts from the reservoir, right? So what, the amount in the reservoir is what comes in minus what goes out. And so the change in magnesium that enters the reservoir, the rate at which it enters the reservoir, I said it's constant, 16 weight percent. So that's just the 5 cubic meters per second, the flux in, times the density to get me to kilograms, times the proportion. So I've got, some kilogram per second of magnesium entering my reservoir, right? That's what I've got. Okay, so you can just do that. The rate at which it leaves the reservoir is equal to the eruption rate. That's 5 in kilograms. That's 5 times 2,800, right? Kilograms, or 14,000 kilograms per second is the eruption rate, times the concentration of magnesium in that magma. Okay, well, the concentration of magnesium in the magma is xt divided by the number of kilograms in the reservoir. Okay, so that gives me 2 equations. It gives me an initial condition, which is how much magnesium is in the reservoir at time equals 0, right? It's the same as the number of rabbits in my population at time equals 0 or whatever. And so I've just multiplied that out. I've got the number of kilograms in the reservoir times the concentration of magnesium gives me the kilograms of magnesium in the reservoir at time equals 0. And then the differential equation, and that's dx dt, the change in x as a function of time. That's the amount coming in per second. And I said the amount coming in per second is 2240. That's this up here, that concentration, minus what's going out. And that's the flux and the mass flux in kilograms per second times the concentration going out, which is x of t divided by the total size of the reservoir, right? So that's dimensionless, kilograms over kilograms. I've got xt in kilograms per second minus kilograms per second equals kilograms per second. Okay, and I can solve this then using my Runge-Kutta approach. And so here's my equation. Now f of tx is not just returning x, it's returning this expression, 2240 minus 14,000 divided by 2.8 e to the 11th times x. That's what that equation returns. And so I'm going to pass my variables to Runge-Kutta. Let me just go down to the main part of the program first. I've got initial conditions, time equals 0. X is the mass of MgO in the reservoir at 0 seconds. I'm going to have an initial time step, just how I had it before. And I'm going to run for some period of time. And that's going to be half a year expressed in seconds, right? So the Y is just going to be Y total. I'm just going to call my Runge-Kutta solver, and I'm going to pass it those variables. So when I go up in here, this is exactly the same expression as I had before. I'm just gonna move through and solve for Y. You can treat that as a black box if you want to. And I find out that my magnesium concentration after half a year is about 12%, right? So that's pretty useful. In fact, people, geochemists can use that kind of thing to sort of model the rate of change in magnesium, to understand things like what is leaking into the reservoir, what may be the volume of the well mixed part of the reservoir or whatever. And then I can modify that just by, here I'm just creating an output by tracking the concentration as a function of time and plotting that up. And so this is just a little quick change in that. And I can plot this graph, which is a change in concentration of MgO in the lava as a function of time. So that's a lot, but it's not that bad, honestly. So think about what's happening here. Next time you want to pass up a differential equation in a paper and say, well, I'm going to ignore that part. You can actually think about how you might solve it. And in this case, a lot of differential equations are like this. If you look at, for example, Sparks' bubble paper, it's pretty much dealing with this sort of level of differential equation when you profoundly influence volcanoes by saying how fast does the bubble grow as a function of time and stuff like that. But anyway, I'm just looking at what goes in and what goes out and expressing that in terms of a mass, right? That's all I'm doing. You could do it in terms of volume or something like that as well if you wanted to, but I just did it in terms of mass and calculated the concentration and plotted that concentration as a function of time. So you can just take that and sort of experiment with how you change some of these parameters in the model, how you might change, you could think of monitoring the sulfur dioxide flux from a volcano as a function of time or something like that, and just do the calculation in terms of mass of sulfur and the amount of sulfur in a primitive magma versus a degassed magma and that sort of thing. I mean, you gain a lot of power just by looking at it in terms of this sort of simple approach. So I'm just going to blast along here. I'm going to go on to another one. Here, we're going to look at the pressure in the magma reservoir and the expected deformation associated with the reservoir as a function of time. And I got this idea from a paper that Kyle Anderson and Mike Poland wrote a few years ago, where it sounds a lot more it is a fancy paper, but they use some Bayesian methods to invert for the pressure in the magma chamber and stuff like that. But the basis of the solution, the forward solution in that problem, is just a series of differential equations. So let's look at that. A main difference between this example and the last example is I'm actually going to develop a couple equations to explain the change in pressure as a function of time. I'm going to start out really simple and almost pedantically simple, honestly. I'm just going to say the change in pressure of the magma reservoir is a function of time. It's going to be a function of shear modulus mu divided by the reservoir volume, and what goes in and what goes out is a function of time. So if Q in is bigger than Q out and mu and V are constant, then the pressure is going to go up. No big deal. And it's a linear equation, so we certainly don't even need a differential equation to solve it. You can just solve that if you know in and out and that kind of thing. But let's just go through the process here. And one thing I want to show you is I'm going to use something called a keyword argument, which is super useful in ordinary differential equations for solving them easily, especially when you've got a number of variables on the right-hand side of the equation. And it's useful generally in Python too, or in any other coding language. So QARGs stands for keyword arguments in Python. And so let's look at that for a second. Let's just go down. A lot of this is sort of the same, but I'm just gonna, now instead of defining all these variables, I'm gonna pass to my function, to my Runge-Kutta function independently. I'm gonna specify them essentially as a dictionary, right? So if you're familiar with that in Python, it's good, but otherwise, I'm just looking at my 4 variables on the right-hand side of the equation. I'm assigning some values to those with time equals 0, and my pressure, my initial pressure is going to be, you know, some value, 50 megapascals or something like that. And I'm going to set my time and my total time length. And then I'm going to run my ordinary differential equation through, in this case, run a 4th order Runge-Kutta solution. So let's go back up here. And we'll look at this in more detail for a second. Deriv is the function I'm solving. And so down here, there's my ordinary differential equation. I'm passing it these variables here, and I'm returning my solution, right? Shear modulus divided by volume flux in, volume flux out. And I call that here, and I pass it quarks. So I'm not going to spend a lot of time on this, but notice what happens is I can pass quarks around like it's a variable, and I can unpack it right here, a reference to a variable technically, or set of variables. And so I'm gonna unpack it here. And so you can look at the structure of that and see how that works if you're curious about it. All it does for me is it shortens out sort of makes the code more readable in here, because I'm just passing all those variables back and forth every time I have to call my function, in this case, the function that represents the right-hand side of the equation. And like before, then I'm just going to create a list of the change in pressure as a function of time. And since this is linear, you can just solve that directly for a given input and output and so on. But I do it here and I solve it, and it's linear in time. So you're like, why did you do all that, Chuck? Well, because I want to just show you the structure of how I solve that solution, because now it could get a little bit more complicated. Now that I've got that relationship, I can break it down. Let's see what's controlling Q out here. So Q out should be a function of the pressure in the magma chamber. So picture the magma chamber as sort of a sphere with some shape in the subsurface. Magma's leaking into it, but magma's leaking out like through a soda straw going to the surface, and that soda straw is going to have flow in it, which must depend on the pressure in the magma chamber itself, right? And so I can use Pouzet flow, Sylvain. Whatever. And or laminar flow, as the rest of the world calls it. But anyway, I can find that expression. So here it's just written for a laminar conduit, a cylindrical conduit, circular conduit and cross section. Sort of a classic equation for what that flow might be as a function of pressure, and in fact the pressure difference along the length of the conduit. So I can sort of approximate that with the second expression, where P naught minus P is the initial pressure and P is the current pressure in the chamber. Okay, so now I've got my sort of ordinary differential equation situation where I've got dp dt on the left-hand side. Here it appears that I don't have any problem because there's no p on the right-hand side, but actually there is a p on the right-hand side once I start looking at that equation in more detail. And a lot of authors do this kind of thing. They show you an equation like that and they say, well, actually, you know, the variable I care about is embedded in here, and here's my second equation. So how do I implement this? Now, like sort of, I got two equations. I could sort of substitute out in there and do it the way I did it before. I'm just going to change that up a little bit. I'm going to say there's two equations here. I just sort of inappropriately called it derivative 2, just because I'm moving along in my notebook here. And I've got another function now called flux out. And so you can see that the volume flux is going to be dependent on flux out. I'm going to pass it these equations. And then derivative 2 is going to return the solution to my original equation now that the pressure depends on that flow rate, or the flow rate depends on the pressure, sorry. And so I'm just going to call the same expression. I'm using quarks again just to simplify things, and I'm going to track the output. And so now when I run this for some initial conditions, I can change I can see what the pressure change is in the conduit as a function of time, right? For these particular conditions of flow in and flow out. So that's pretty cool. And then all I do is I solve for Moghi's solution for the vertical displacement associated with the pressure in the magma chamber. And if you're not familiar with Moghi's solution, have you guys talked about that already? Maybe? I don't know. But anyway, you can calculate the maximum. Okay, you can calculate the maximum displacement. That's how much a GPS or a satellite would measure the displacement at the surface given a change in pressure in the magma chamber and some geometry. This is sort of like the maximum change I would expect to see as a function of time. So if I plot that, now I'm solving the differential equation using the laminar flow approximation and then plugging that pressure into Moghi's model, and I get the displacement, the maximum displacement I expect to see as a function of time. So what Poland and Anderson did in their paper is they said, well, we want to explain displacement that we see as a function of time in terms of pressure changes in the conduit that result from this kind of simple tank model of input and output into the conduit. And so this is pretty clever, but and I think their paper is very clever, but what they do is they build this model step by step by step, starting with that sort of first basic model I showed you before, adding some complications like the way things flow through the conduit, and then linking in some other parameters like what we observe at the surface. And so that's sort of the structure of the way scientists, volcanologists pursue these kinds of problems. And you can see this kind of approach over and over again in work, by, like I said, Macedonio and Woods and people like that. So it's very clever, but I just want to like convince you it builds step by step, and you can probably do this too. And then the third notebook, which I'm not going to talk about because I'm running out of time, is solving for ballistic transport. And so you can check this out, how you use the Runge-Kutta solution to solve for ballistic projectiles. And so basically the idea is if you have a ballistic transported from a volcano, how far is the ballistic going to go given its initial velocity and stuff like that. It's got two governing equations. It's got a governing equation for the rate of change in the horizontal and vertical velocity as a function of time, and that depends on a drag coefficient, which is here just shown as beta, and the velocity squared at time. So the velocity is the rate of change in velocity in the horizontal direction depends on the square of the current velocity times the drag coefficient. And same for vertical, except gravity also acts on it in that direction. Okay, so you can solve these things exactly the same way. I'll just really quickly show you the equations. So here's the two equations for the horizontal and vertical component of velocity. No big deal. You can get in the literature and see how these equations are derived and how people can complicate those equations a little bit. No big deal though. So I specify some initial conditions. I specify X. I specify my quarks, which in this case is just beta and gravity. I specify my total time, and I let it run. I let it rip, and the long and short of it is I can plot the vertical distance and the horizontal distance. That's the trajectory of the projectile as it leaves the volcanic vent at 0, 0 and heads out. And you can see it's asymmetrical because of drag in the atmosphere. And so the seemingly complicated problem of ballistic transport reduces to a pretty reasonable kind of solution. So I skipped that, but if you're interested in ballistic transport, you can go through that in detail and mess around with it. And then you can begin building a complicated model if you want. So people express the equations like that. I don't know, there's like 10 papers expressing the equations like this, and you can check those out and see that it's not magic how they solved it. Most of them use Runge-Kutta, some of them use Euler's solution, and you can model whatever you like that way. So that's it. That's super quick. Sorry about that, but I'm just trying to give you a taste of how this works and what you might get out of it. And I encourage you to explore some of these relationships. You can look at conduit flow. You can look at, geochemical changes observed by remote sensing. You can look at vertical deformation at the surface of the Earth. There's a lot of commonality in these problems. Of course, the ordinary differential equations work by making simplifying assumptions. You have to kind of decide if that's okay for your problem or not. A lot of times it is okay to give it a shot, and people have gotten a lot of mileage out of it. They've solved a lot of problems, like Macedonio and colleagues had a nice paper where they took that laminar flow model. They included some turbulence. They looked at the coefficient of erosion of the conduit, so the radius changed as a function of time, and solved that ordinary differential equation. So it's all kind of achievable if you take it step by step. Draw yourself a picture of what's going on. Try to define the variables. Try to use Runge-Kutta if you can, because it's so straightforward to apply in a lot of these circumstances. So that's it. I'm sure there's no questions. Sorry about that. But anyway, let them rip.
I have a question for you, Chuck. So
Sure.
at the beginning, you mentioned how using different methods, we're actually, getting closer to the exact solution or not. So
Yeah.
Sometimes, most of these models, they already come with a way of solving the partial differential equation that is already included in the model. But maybe sometimes the data we have can actually be used as an exact solution that maybe another method is going to fit better the data we have. So, you know what I mean? So, for example, the Runge-Kutta method can be good for some data, but then for some other data we have, then maybe applying another method would be better. So, and that's something
sure.
Most of the code don't give us the option, right? Of choosing which method. I know one or two code that can you can choose as an input, you can choose the methods, how you want to solve the partial differential equation, like a first order or second order. But some of the codes don't do that. So
right. Right.
I think it's good
It's
to
it's
remember
kind of
that.
up to the person writing the code, but so first of all, when you have the data, like the time series itself, so say somebody walks up a lava flow, simple sheet lava flow, they walk up it and they see the change of geochemistry as a function of position, and they say, oh, that's a change in geochemistry as a function of time. So you have that series. You can then invert to try to find a solution for, say, the volume of the reservoir, right? And so people try that. That's what Anderson and Pola do in their paper. They use a Bayesian inversion to estimate what's going on, but they still solve the Ford solution using Runge-Kutta, right? The Ford model is still Runge-Kutta, I think, in their paper. Yeah, sometimes you can use an analytical solution. So for example, TEFR2 solves a differential equation using an analytical solution. And it does that we did that by imposing a lot of limits on what it can solve. So you have to observe those limits in order to solve it. So yeah, I mean, it's a decision. It's either up to the person who wrote the code usually, or sometimes they give you options, but it's up to whoever wrote the code for sure. That's why it's interesting to use these notebooks to try to write your own code, because you can do whatever you want.
and you can maybe find a method that is actually fitting better your data, right?
Right, exactly. A lot of times, you don't want to the uncertainty in your data kind of means that you don't really need you don't even really need Runge-Kutta, a fifth order Runge-Kutta. Maybe you can just use a second order and it's fine. I mean, it doesn't matter. You can, since they're all implemented, you can use the fanciest one and reduce your uncertainty, but maybe it's not really warranted at the end of the day because of uncertainty in your data.
But maybe you can save on computational time, right? So basically, if you have the data and you say, oh, I just need a second order, so I'm just going to use a second order, and then your code run faster, right? Because that's the issue of like increasing the order of the Runge-Kutta, then your code is running longer, right?
Right. But for a lot of problems, it doesn't matter. So
yeah, true.